All right, so we're going to talk about reaction types and what do we need to look at to identify a reaction type. The first thing we're going to do is we need to look for the most obvious reaction type. The most obvious reaction type is combustion. And so is O2 a reactant? And notice that's O2 all by itself. Okay? If you can see O2 as a reactant, you know, yes, you know you have a combustion reaction. We use a shortcut there, and instead of writing out all of combustion, you'll often see me write a capital C. Do be careful doing that in Word, though. I think Google Documents does this too. It'll change that to a copyright symbol if you're not careful. If O2 is not a reactant, then we go to the next question. And you ask, are there more reactants than product? I'm going to abbreviate product there. If there are more reactants than products, then what you have is a synthesis reaction. And that is abbreviated with a capital S. If there are not more reactants, well, are there more products? Do you have more product than reactants? If you've got more products than reactants, then you've got a decomposition, which I'll abbreviate, but I'll also abbreviate even smaller. It's a capital D. If there aren't more products, is there a lone element on each side? Is there a lone element on each side of that arrow? If there is, yes. Yes, if there is, then it is single replacement, otherwise known as SR. And I need a little tiny bit more room. Here we go. If there's not, no, well, this one should be, are there two compounds on each side? If there are two compounds on each side, just two compounds, are there, I should put the word just in there, just two compounds on each side, then chances are you are looking at a double replacement. That would be DR. And if that's not true, then that means none of the five are in there, and you are looking at a redox, which abbreviated capital R. So, how do we determine a reaction type? So let's say we're looking at a reaction like this one right up here. N2 plus H2 gives you NH3. I ask, is oxygen a reactant? I'm going to do this one in blue. Let's look at this one in blue. In blue, is oxygen a reactant? No. So we go down. Are there more reactants than products? Yes. So that tells me that we have a synthesis reaction. So we'll put an S on this one. All right. Let's do this one in red. The second one example here will be done in red. There we go. All right. So this one's in red. Is O2 a reactant? No, it is not. Everybody's like, oh, wait, but there is an O2. No, that is not an O2 all by itself. This O2 over here is a product. There's an O2 in there, but it's a product, not a reactant. So O2 is not a reactant. Are there more reactants than products? Well, no, we have 1, 2 reactants and 1, 2 products. So no. Are there more products than reactants? No, we just said they're 2 and 2. Is there a lone element on each side? Well, I've got a lone element here, but there's not a lone element over on the left-hand side. So no. And are there just two compounds? Well, we've got a compound here and a compound here. But over on the right-hand side, there's a compound and then an element all by itself. That is not correct. So this is not the double replacement. This one must be a redox reaction, R. This one is R. Real quick, to jot down one more. All right, I'm going to jot down NaCl plus AgNO3 yields NaNO3 plus AgCl. Pause. See if you can identify the type. If you said that this one was combustion, it is not combustion. There's no O2. It is not synthesis, because it's the same number of reactants and products. It is not decomposition, because same number of reactants and products. Same thing for both of those, right? It is not single replacement, because there ain't no element all by itself. All these elements are all paired up, some of them with two other elements. It is, in fact, a double replacement, because there are two compounds on the left and two compounds on the right. That's how you do this.